Now, I begin by sharing this exercise for that. This is from the last session, so that at your own time you can try to do these questions where we are solving this is a modular arithmetic. So you are solving, for example, in this first question, we want to find the value of x. So that's what we could do, what you do later. So you'll try, and then if in case you get any problem, then we will discuss it during our Thursday class. So today I want us to look at how to find inverses in modular arithmetic. Oh, this is a continuation of the exercise. So this is question 3. Of course, you'll see these questions in the notes that I sent. So I want us to look at how to find inverses in modular arithmetic. And I'll be using the extended Euclidean algorithm to do that. And then later in the same, I think today we shall look at how to use Fermat's little theorem to find inverses. Now you need to know what an inverse is just from the very beginning. For instance, if I talk of the inverse of A to be B, then I mean that the product of these two will give us 1. That is, so that means that B is the inverse of A, or A is the inverse of B. So that if you understand that from the very beginning, then it becomes very easy for us. So that if I'm given an equation, AX is congruent to 1 mod M, and then here, what it means here that these two are inverses of each other. A is the inverse of X, and X is the inverse of A. That is why you're saying that their product has given us 1. Now, a very important thing for us to note before we begin, when do we say that A has an inverse mod M? So for A to have an inverse mod M, then A and M must be relatively prime. Must be relatively prime. So if they're relatively prime, then A has an inverse mod M. What I mean by relatively prime, as we said earlier, is that I mean that the GCD of A and M must be 1 for this A to have an inverse. For this A to have an inverse mod M, then the GCD of A and M must be 1. So we use the word relatively prime, as we said earlier, or we can use the word coprime. That A and M must be coprime for A to have an inverse. So I think that is what we need to know, so that we now begin to find inverses. So let's look at the first example. So the first example is here. We're supposed to find the inverse of 7 mod 19. So as I already said, for us to have an inverse of 7, then 7 and 19, first of all, must be relatively prime. That is, the GCD should be 1. Otherwise, you cannot find the inverse of 7. But since these two have the GCD of 1, and therefore you can find the inverse of 7. Now, so I've written it this way, that find the inverse of 7 mod 19. Somebody else will have written it this way, and it means the same thing. It means the same thing. That find the value of X, which when multiplied by 7 gives you 1. Find X so that 7 times X will give you 1. It means the same thing. It means find the inverse of 7. Because we know that it's only the inverse of 7, which when multiplied by 7 will give you 1. So these two questions mean the same thing. So we now want to solve using the extended Euclid algorithm. So we begin by, first of all, ascertaining that GCD is 1, that the GCD of 19 and 7 is 1, as we did earlier. So you would ask ourselves, how many times does 7 go into 19? Goes there twice, and the remainder is 5. Then what about 5 into 7? How many times? So 5 will go into 7 once, and the remainder will be 2. What about 2 into 5? Then it will go there twice, and the remainder will be 1. We've arrived at the GCD because the next step gives us a remainder of 0. The next step gives us a remainder of 0. That means our GCD is this. Our GCD is 1. So we've ascertained that the GCD is 1. So after that, we use the extended Euclid's algorithm as we did earlier, make 1 the subject of the formula. That is why from the very beginning, I said that the extended Euclid's algorithm is very important as we go forward. So we make 1 the subject of the formula. We know how to do that, but let's just repeat for the sake of that. So we make 1 the subject of the formula. This is the 1 I want to make the subject of the formula. What does it equal to? So I take this on the other side. I can see that 1 equals to 5 minus 2 multiplied by 2. Then I substitute this 2. This 2 was the remainder, this remainder here. What does this 2 become? This 2 is the same as 7 minus 5 multiplied by 1. So what I have here is that 1 is equals to 5 minus, instead of this 2, I write 7 minus 5 multiplied by 1, and then close a bracket, there's that 2 outside. Then when you do this, open the bracket. Before that, I have this 5. And then now open the bracket, there's this minus outside, and there's this 2. So when I take them inside the bracket, multiply by 7, I would have minus 7 multiplied by 2. And then multiply them by this 5. There's a negative here. There's this other negative. That give us positive 5. Then 2. The like terms together, the 5. Let me write first of all negative 7 multiplied by 2. And then the 5 put together, I have 5. Then that gives me 3. So now I'm left with this 5 to substitute. And I substitute, it's here. So I substitute by its equivalent, which is 19 minus 7 multiplied by 2. So what I then get is negative 7 multiplied by 2. Instead of this 5, I write the equivalent. Instead of this 5, I write its equivalent. And its equivalent is 19 minus 7 multiplied by 2, then multiplied by 3. Then multiplied by 3. Now, so when you do that, what you arrive at is this. This is what you arrive at as after collecting like terms. You arrive at this equation here. So what we have, therefore, what we've arrived at is 1 is equal to 19 multiplied by 3, then minus, no, plus 7 multiplied by negative 8. Now, so the question is, this was the question. The question was, what can you multiply by 7 to get 1 mod 19? That was the question. What can you multiply by 7 to get 1? And I'm saying it here. The 1 is here. What I multiply by 7 is this, negative 8. Negative 8 has been multiplied by 7 to give me 1. So that means the inverse of 7 is negative 8 mod 19. But this is a negative number, so we make it positive. We ask ourselves, and we did this one on Thursday, the easiest way we're doing that, we're just adding this value here plus the value here. If the value here is smaller, if the value here is smaller, we're adding it to 19. And you remember when the value here is bigger, what we were doing, and we shall see if we were to come across that. So that means if I add, what I get is 11. So the inverse of 17 is 7, or the inverse of 7, therefore, is 11. That's how you get the inverse. It is 11. And so when you try, you can try later and see whether it's true. Just multiply by 7, multiply 7 by 11, mod 19, and see what you get. Of course, this is 77, mod 19. So if 19 were to go there, the remainder would be 1. The remainder would be 1. So that's how I want to take one more example, how to get the inverse. And once you understand how the Euclid's extended Euclid's algorithm, becomes very easy because it's the same thing we are doing repeatedly. Let's look at the next question. We want the inverse of 364. And you remember that these values can become larger and larger. And that is why a use of a program or an algorithm is always very important. These numbers can become larger and larger, and even this one can become larger and larger for you to get the inverse. Now, so we want a number which, when multiplied by 364, gives us 1. That's what this question wants. The inverse of the same question as find the inverse of 364. Mod 765. It's the same thing. Now, so we use the Euclid's algorithm first of all to ascertain that the GCD is 1. So we ask ourselves 364 into that. What is the remainder? Then this remainder into 364, 9 times. The remainder will be 31. 31 into 37, once. The remainder will be 6. 6 into 31, 5 times. The remainder will be 1. This is our GCD. Then reverse. Make 1 the subject of the formula. So 1 will be the same as, just reverse this. Just repeating for the sake of anyone who might have forgotten, this will be the same as this. Then now, replace the next remainder. We've replaced the first remainder. The first remainder is that. Now the second remainder, going up, the next remainder is this 6. It's the one we replace here. So what I have is 31 minus, instead of 6, this 6 can be written as 37 minus 31 multiplied by 1. And then there's this 5. Now we know how to do this process. We've done this before. So you'll arrive at this. You'll arrive at that. So this is, I want to pick it from there. I want to pick it from there. So I show you how to get the inverse. Once you arrive at a point where you have now 1, the final stage, you've written 1 as a linear combination of 765, negative 59, and then plus 364, multiplied by 124. Now, the question was, what can you multiply by 364 to get 1? What can you multiply by 364 to get 1? And I can see what I've multiplied by 364 is this, 124. That means the inverse of 364, therefore, mod 765 is 124. That's the inverse. Now let's look what I think those two examples are enough for us to now to get the inverse using the Euclid's extended Euclid's algorithm. And later on, I'll be showing you how to do the same questions now using other methods like the Fermat's little theorem and the Euler-Phi theorem, so that you are equipped with the several methods or techniques of finding inverses. Now, once we have inverses, we can also solve systems or equations of this nature. And we did these questions on Thursday, but we're using the extended Euclid's algorithm. But we can still use inverses. We can still use inverses. So that means if I'm given an equation like this, I'm only supposed to get the inverse of 7. And then once I have 7x is equivalent to 3, congruent to 3 mod 19, and I have the inverse, multiply that inverse on both sides. I multiply let me say the inverse is p. I multiply it on the left side and multiply it also on the right side. Now I know what this will give me because it's a number times its inverse. Supposed to give me 1. A number times its inverse supposed to give me 1. And then x. And then what I have here is 3b. This is 3 and then this is b, mod 19. So of course the left-hand side has an x. 1 times x is just x. And then this one, I'll reduce it, mod 19. I'll reduce it mod 19. So let me just do this question. But that is the explanation, that you must know that when you multiply a number times its inverse, what you get is 1. So 7 times b, supposing b is the inverse of 7, then this product is supposed to give us 1. Now, so we've already found the inverse of 7 in our previous example. And the inverse of 7, which we've just done, the first example we did, gave us 11. 11 was the inverse. So once you have that, then you take 7x is congruent to 3 mod 19. And multiply by this inverse on both sides. Multiply by the inverse on this side and multiply by the inverse on this side. Now these two, 7 times 19, 7 times 11, since it's a number times its inverse, we know it will give us x, 1, it will give us 1. So 1 times x gives us x. And then this other one is 33, mod 19. But 33 is a very huge number, is bigger than 19. So we reduce it. We reduce it, we get the remainder. So that means the x there is 14. The x is 14. So when you reduce, when you only divide 19 into 33, and then write the remainder. 19 into 33, the remainder will be 14. Just a minute. Yeah, so let's look at the next example. So you see that if you are using the extended Euclid's algorithm to find the inverse and then solve, that means you'll already have gone beyond, you'll have gone past the answer. And then you're going back. It's just like going back again. Let me just show you what I mean using this example. Now look at this question here. This question, I have 8. So I already said that for us to get the inverse of this number, it must be relatively prime to 26. But when you look at 8 and 26, they're not relatively prime. So that means you cannot find the inverse of 8 mod 26. You cannot find it. So, but we're supposed to solve this question. So that means, as we did earlier, since 2 is a common factor, you divide it through by that common factor first of all. So 2 is a common factor here. So divide it through by 2. And when you do that, you get 4x is congruent to 6 mod 13. At this point, you now realize that the GCD of 4 and 13 is 1. Therefore, we can find the inverse of 4 mod 13. You can find the inverse of 4 mod 13. So that inverse of 4 mod 13 is what you get. Then use it to solve this equation. Once you've solved this equation, you come back and solve this one. Now, let me remind you again what we did earlier. For us to solve this equation, this original equation, what we did earlier, we were finding the GCD, first of all, of 8 and 26, and this GCD is 2. So that means, and 2 divides this 12. So that means this original equation has 2 solutions. The original equation has 2 solutions because the GCD was 2. So it will have 2 solutions. So, but we've reduced it to get this equation first of all. So this equation will give us one solution. Then we go back as we were doing in the previous examples and get the remaining solution for this equation. So let me just now go straight to the working. Now, so after realizing that 2 was the GCD and that 2 will divide it 12, I said this system would have 2 solutions. But then I divide, first of all, the entire equation by 2, which is the GCD, to get this. I call this equation 4. Then it's this equation that I use the Euclid's algorithm by asking myself, how many times does 4 go into 13? And 4 goes there 3 times. And the remainder is 1. So we cannot proceed because we've already reached the GCD. We just make this one the subject of the formula. This one, therefore, is the same as 13 minus 4 multiplied by 3, which we can also write as 13 plus 4 multiplied by negative 3. And so I want the negative to be with the 3, not 4, because 4 was positive. So 4 has a positive sign. And the 13 also has a positive sign. And so what that then means is that the inverse of 4 is that number which I'm multiplying by 4 here. So the inverse of 4, therefore, is negative 3 mod 13. And this, since it's negative, we write it as positive. As we said earlier, I add this to that. That gives me 10. So this is now the inverse. I want it to be positive because always the remainder has to be positive. So it's 10 is the inverse of 4. Now, since I have this 10, I now go back to this equation 4 here and find the value of x. I had 4x is congruent to 6 mod 13. But now the inverse of 4 is 10. So I multiply both sides of this equation by 10. So 10 multiplied by 4 multiplied by x would be the same as 6 multiplied by 10 mod 13. I know what 10 times 4 gives me because 10 is the inverse of 4. So 10 times its inverse would be 1. Then times x, that'll give me x. And this is 60 mod 13. I'm asking myself, if 13 were to go into 60, what will be the remainder? And I would get a remainder of, is it 8? I'll get a remainder of 8. Because 13 into 60, 13 times 4 will be 52. So 13 will go into 60 4 times, and the remainder will be 8. So this is the solution, the first solution. This is the first solution of x. For us to get the second solution, we do it the same way we did on Thursday. We say to get the second solution. So the first solution we found to be 8. So the second solution, therefore, would be 8 plus this mod plus this 13. That gives us 21. So those are the two solutions to our original equation. Those are the two solutions to our original equation, 8 and 21. So we've used the inverse to solve a congruence equation. I'll take one more example, and then we'll look at the Fermat's little theorem, another method of finding the inverse. I want to solve this. Now, so the GCD, I begin from there. The GCD of 51 and 87 is 3. So that means we cannot find the inverse of 51 mod 87 because they're not relatively prime. For them to be relatively prime, we said the GCD should be 1. So since the GCD is 3, we cannot find the inverse of 51. So what we only realize from here is that this means that this equation has 3 solutions. Because this 3 can divide 6. Because this 3 can divide 6. So this system has 3 solutions. Now, we divide through by this GCD. And when you divide through by this GCD, you get 17x is congruent to 2 mod 29. So you notice from here that 17 and 29 have a GCD of 1. And so we can find the inverse of 17 mod 29. So we proceed and get that inverse. We proceed and get the inverse, and we do it using the extended Euclid's algorithm. First of all, by Euclid's algorithm, where you are dividing 17 into 9 and noting the remainder. 17 into 29, the remainder will be 12. 12 into 17, the remainder will be 5. 5 into 12, the remainder will be 2. And then 2 into 5, the remainder will be 1. And then you reverse, you make 1 the subject of the formula. You make 1 the subject of the formula. So you're beginning from here going up, beginning from here going up. Now this process, I noted on Thursday that most of you have grasped it, so I don't need to repeat it. So let's just go straight to my working. So when I come to, so I'm making 1 the subject of the formula, and you arrive at this. you arrive at this, which you then just rewrite to mean 1, and you want to maintain this 29 to be positive. And so I'll have -7 there, and then plus 17 multiplied by 12. Multiplied by 12. Let me just write properly there. 17 multiplied by 12. And so what is the inverse of 17? The inverse of 17 is that number multiplied by 12 to give you 1. And that number is 12. The inverse of 17 is the number multiplied by 17. The number multiplied by 17, which is 12, to give you 1. So the inverse of 17 is 12. It was mod what? Mod 29. Now, so multiply by this 12 on both sides of the second equation. Let's just go back. That is 12. We've noted that the inverse there is 12. So let's go back to where the equation was, that we see what it is. The equation is here, equation 5. The equation that we got after dividing through by the GCD. So it is this equation that we multiply by 12 on the left side, and then also by 12 on the right side. And when you, this left side here, this will give you 1. 1 times x will be x. And then 2 times 12 will be 24 mod 29. Now this system had to have 3 solutions. So the first solution is what we've just got as 24. So the second solution will be 24 plus 29. And then the third solution will be this 24 plus 29 plus another 29. So this will be the third solution, and you make sure that they are less than the mod. Make sure that they are less than the mod. And I think they are less than the mod. So they don't require reducing because they're already less. So that is what I did. That's what I did. And when I did that, I got 24 as one result, then got 53 as the other, then got 82 as the other. So there are 3 solutions. Now, you can also be given this, also be given a question like this to solve. And so there are 2 ways. So we did solve this question, a similar question earlier. Now, I've written here something. I've said that recall that to work with fractions A out of D, to work with such fractions, mod M, the denominator should be relatively prime to M. The denominator here, this denominator should be relatively prime to M. Now, so what I did here, just as we do it in other mathematics, which is not congruence, as we do it, we would multiply by 7 on both sides. So when you do that, on the left side, you left with 5x, and on the right side, you have 84 mod 19. So this 84, then you reduce it mod 19. And I was doing that, I did that, and found that 19 going into 84, the remainder will be 8. Now it's now easier. We see that the GCD of 5 and 19 is 1, and therefore we can get the inverse of 5 mod 19. We can get the inverse of 5 mod 19, and that's what I'm doing here. That's what I'm doing here by the Euclid's algorithm, and then reverse using the standard Euclid's algorithm you arrive at this. So we have that 1 is 19 multiplied by -1 plus 5 multiplied by 4. We wanted the inverse of 5. So the inverse of 5 is 4. So the inverse of 5 is 4 mod 19. Now, after finding this inverse, multiply it on both sides of this equation. Multiply it on both sides of this equation. So 5 times 4, then this side, oh, the reduced one. The reduced one is here. The one that has 8. So 5 times 4 will give us 1. Then times x will give us x. And then 8 times 4 will give us that 2. Mod 19. Then reduce this that 2. Mod 19. The remainder is 13. The remainder is 13. So x is therefore 13. I think those examples are enough on solving this kind of questions. And I want to introduce something slightly new, but what is very important also. We've been talking about inverses, and we've already stated that for us to get an inverse mod m, the inverse of m mod m, if that is to happen, let me just write that. I said that for us to get the inverse of a mod m, for that to happen, then the GCD of a and m should be 1. Now, supposing we are dealing with a group and a group has several elements. And the question is, how many elements would have inverses in that group? That's the question. Supposing we have several elements that are given to us, we are talking of mod m. Let me show you what mod m means. When I'm talking of mod m, what do I mean? When I talk of mod m, I mean this is a set of elements 0, 1, 2, all the way up to m minus 1. Those are the elements mod m. For example, when I talk of z mod 5, so how many elements does this group have? This group has elements 0, 1, 2, 3, then 4. They go up to 5 minus 1. So the question is, how many elements here have inverses? That's what I'm introducing. How many elements have inverses in a given group? And the group that I want to look at is the group of units. The group of units. And the word I've used is units. What do I mean? Units of this group. Let me just use the group I've used. The group I've used above was Z5. So the units of this group are elements. Let me say, for instance, A is a unit in this group if A and M, and our M is 5 this time. Our M is 5. So A will be a unit here if the GCD of A and 5 is 1. And so we say that 1 here is a unit. For instance, if I'm talking of Z8, what are the units of Z8? Those are elements which are relatively prime to 8, and those include 1, 3, 5, and 7. They must be less than 8 or equal to 8. units of 8. Units of 8 are elements less than 8, which are relatively prime to 8. So when I talk of units of 9, and I'm looking at this group, so the units of 9 will be elements which are relatively prime to 9. And there are 1, 2, 3 is not, 4 is, 5, 6 is not, 7, then 8. Those are elements which are relatively prime to 9. And we already said the relatively prime means the GCD is 1. Now, so a group of units, a group that consists of elements which are relatively prime, I'll denote it by UN. UN, I've said, UN is a set comprising of elements A such that the GCD of A and N is 1. The GCD of A and N is 1. So this is a group comprising of only units. So this is how I'll be denoting it. So for instance, when I write U5, what do I mean? And you say, when you read some books would be writing it something like this. Some books would be writing it something like this. And then MZ, and then they put a star here. They put a star here. And you see, they have already defined what the star means. They have already defined that a star means that these are a group of units. But for me, what I understand, when I just put a star, normally I understand that a star means without a 0. But if the book has already defined that their star means a group of units, and if you are reading that book, then that is the definition. So it's always very good when you're reading these books, you know what the symbols mean. So books will begin by defining the meaning of their symbols. So for instance, a book would define this way. But another book would say that if it writes like this, it means this group, what it lacks is only a 0. What it lacks is a 0. Some book would define it that way. And that is why I've now defined mine. I've said, and some books also use this, that the group of units is, we use U, then 5, for instance. That means the elements inside this group are those which are relatively prime to 5. Those which are relatively prime to 5. And this is that. So U5 means this. Now, what is now important is this. What is important is what I've written here. Where have I written it? I've said, okay, before that, let's just see what I've done here. This is, I want to multiply elements of U5 in this table. And then in this table, I'm multiplying elements of U8. U8, you know what it is. Elements which are relatively prime to 8 are 1, 3, 5, and 7. You want to multiply them, and you multiply them mod 8. And then in this other table, the Kelly table, we'll be multiplying elements of U8, U5. What are these elements? Those which are relatively prime to 5 are 1, 2, 3, and 4. There's something you note here, and I'll come to that. When the number here is prime, like 5 here is prime, how many elements do we have? 5 minus 1. 1, 2, 3, 4. 4 elements, 5 minus 1. When the number here is prime, the number of elements inside this group are, if n is prime, if p is prime, it will be more, p minus 1. But if the number here is not prime, I'll show you how to find how many elements do we have. because that will be very important to us going forward, how to find number of elements which are relatively prime. Let's go straight to multiplication. I want to show you how to multiply these elements. And we already know how to multiply, but I just want to emphasize that in this table, we are multiplying elements of U8, U5. So we are doing it mod 5. So 1 times 1 will be 1, 1 times 2 will be 2, 1 times 3 will be 3, 1 times 4 will be 4. We are done with that. 2 times 1 will be 2, 2 times 2 will be 4, and 2 times 3 will be 1. Because that was 6, but we are doing it mod 5. So 6 mod 5 is 1. And then 2 times 4 is 3. Because that was 2 times 4 is, of course, is 8. But we are doing it mod 5. So that gives us 3 as the remainder. So what is inside this table is the remainder. Let's see, 3 times 1 will be 3, and 3 times 2 will be 1. Because it was 6. 6 mod 5 is 1. Then this will be 9 mod 5. 3 times 3 is 9 mod 5, which is 2, which is 4. And then 3 times 4 is 12 mod 5, which is 2. Because 12, 5 into 12, the remainder is 2. So what I've written there is the remainder. So we know how to do this, and we've been doing it before. So let's multiply mod 8. Mod 8. 1 times n of this will just be those elements, so there's no problem there. 3 times 1 will be 3. 3 times 3 will be 1. Because it's supposed to be 9, but 9 mod 8, the remainder is 1. Then the next one, just a minute. Let me erase this first. Okay. The next one is 3 times 5, which is 15, mod 8. So the remainder is 7. And then 3 times 7 is 21, mod 8. So 8 going there, you get 16, and the remainder there is 5. So that's what we are doing here. That's how you multiply these elements. Now, the question is, are you seeing inverses? For instance, what is the inverse of 2? The inverse of 2 is that element multiplied by 2 to get 1. The inverse of 2, therefore, is 3. The inverse of 2 mod 5 is therefore 3. Because 2 times 3 gave us 1. What about the inverse of 3? Is that element multiplied by 3 gives you 1. And what element is that? It's 2. Because I can see 3 times 2 gave us 1. What is the inverse of 4? The element multiplied by 4 to give us 1 is 4. So the inverse of 4 again is 4. So I'm just showing you how to use this table again. If you have this table, you can still get inverses. For instance, here the inverse of 3 is 3 because 3 times 3 is 1. The inverse of 5 is 5 because the 2 gave us 1, the product gave us 1. The inverse of 7 again was 7 because the product gave us 1, and the inverse of 1 is 1. So this is how you get those inverses. And of course, we know how to get inverse. Now, so of this group, mod 44. Just U24. These are elements which are relatively prime to 24. The elements which cannot divide to 24, they're relatively prime. So 1 is one of them, 2 is not, 3 is not, 4 is not. So these are the elements. They are relatively prime to 24. Now the question is, how many are they? Supposing you didn't want to list. Supposing you didn't want to list. I had already answered that question. And I had said that if this number here is prime, then we'll just take that p minus 1, and we know how many they are. We know how many they are. For example, if p is 7, we just take 7 minus 1, and then say that these elements would be 6. But now this number here is not prime. How do we find out how many they are without listing? Because it can be a very huge number with 1,000. You cannot list all of them, then count. Now, so what you would do then is what we did earlier, factorize this number. And factorizing is very important. Factorizing any number is very important. So you factorize. And when you factorize 24, 2 goes there 12 times. And 2 goes here 6 times. And 2 goes there 3 times. And then 3 goes here once. So you realize that 24 is the same as 2 raised to 1, 2, 3 times 3 raised to 1. Now, this is not very important. What is very important here is that 24 has 2 prime factors. That is what is very important to me here in this exam. 24 has 2 prime factors. And the 2 prime factors are 2 and 3. So for me to get how many numbers are relatively prime to 24, what I would do, after knowing that it has these 2 prime factors, I would take the first prime factor, 1 out of the first prime factor, subtract from 1. 1 out of the first prime factor. Then multiply 1 out of the second prime factor, subtract from 1. 1 out of the second prime factor, then subtract from 1. The result multiplied by 24. So this first one is a half, and this other one is 2/3. When you multiply by 24, what you then get is what? What you get, 2 goes here 12, and this is like 6. The number here is 6. So 6 will go here 4 times. So 4 times 2 give you 8. Give you 8. So there are 8 numbers. Let's just count. 1, 2, 3, 4, 5, 6, 7, 8. So that means you don't need to list all these numbers. If the question is just how many they are, you don't need to list. You just find out if P is prime, and then it will be P minus 1. It will be P minus 1. But if P is not prime, then factorize this number. Find out what prime factors are there. The first prime factor over 1 over the first prime factor, subtract from 1, multiplied by 1 minus 1 out of the second prime factor. There can be several prime factors. So continue doing this. Continue subtracting their inverses from 1, or their reciprocal from 1, and so on. Then multiply the number. Now, so what I've just done is what we call, in this second definition, I've defined it as the Euler-Phi function. The Euler-Phi function is what I've just been doing. And I've said the Euler-Phi function, which we denote as this, and some books denote it this way. Some books denote it as this, and others denote it as this. They mean the same thing. So I've used this second one. The Euler-Phi function of n is the number of positive integers less than n, which are relatively prime to n. Relatively prime. The number of positive integers less than n and relatively prime to n. That is what we call the Euler-Phi. So I've already shown you how to do it without necessarily having to count, to list the elements and then counting. But for smaller numbers like 1, that one you can just list. You see, for 1 is slightly unique. 1 is slightly unique because we say that the Euler-Phi of 1 is 1. So you'll find out why. You'll find out why the Euler-Phi of 1 is 1. Yet the Euler-Phi of a number is supposed to be positive numbers less than that number, which are relatively prime to that number. The Euler-Phi of 2 is also 1. This one we know. It's, of course, the numbers less than 2, which are relatively prime to 2, are just 1. But now you find out why the Euler-Phi of 1 is 1. The Euler-Phi of 3, again, these are numbers which are relatively prime to 2, not to 3, and they're less than 3. There are 2 of them. In fact, it's 1 and 2. So Euler-Phi of 3 is 2. That means we have 2 numbers relatively prime to 3 and less than 3. What about Euler-Phi of 4? How many numbers are they? So there are we have 1, and then we have 3. So there are 2. What about Euler-Phi of 5? 5 is now a bigger number. I don't need to list. I only need to know that it is a prime number. So it's p minus 1. What about Euler-Phi of 7? Euler-Phi of 7, I only need to know that 7 is a prime number. So the Euler-Phi of 7 would be 6. That is 7 minus 1. What about Euler-Phi of 13? 13 is a prime number. So it will be 12, no, 13 minus 1. If you list them, you'll get 12. Because all those numbers will be relatively prime to 13. All these numbers, all the way up to 12, they'll be relatively prime to 13, and there are 12 of them. What about Euler-Phi of 14? That's a big number. Now, I use my formula. This number is not prime, but 2 goes there 7 times, and 7 goes there 1. So 14 has 2 prime numbers, prime factors, has 2 prime factors. And what are those prime factors? 2 and 7. So to get Euler-Phi of 14, I would take 1 minus a half multiplied by 1 minus a root of 7, then multiplied by 14. This is the same as a half times 6 out of 7, then times 14, which is 6. And that is why I get, whenever this, if this number becomes larger and larger, then these formulas come in handy. Now, so I've used this parallel lines to mean how many do we have. For instance, if I write U of 5, between those 2 parallel lines, I just mean how many elements are in this group. And this group has 4 elements. This group has 4 elements. The numbers relatively prime to 5 and less than 5 are 4. So I can write this one again. The question is, this group of units of 14, how many elements does it have? And we found the answer to be 6. So those parallel lines, they mean number of elements. We shall also use it to mean order. You see, when you talk of the order of a group or order of a set, what we mean is the number of elements in that set or the number of elements in that group. Now, so I've put the table here, and the table is just giving us the number of elements relatively prime, and we've already shown that the number of elements relatively prime to 14 are 6, relatively prime to 13 will be 12, relatively prime to 12 will be 4, and so on. What is important is the formulas I've given here. I've said that if n is prime, then this formula will be using it. But if n is not prime, then you factor n and find out how many prime numbers, how many prime factors are in n, how many prime factors. If you find that we have P1, P2, P3, up to Pk prime factors, then this is how you do it to get the number of elements that are relatively prime to n. So it would be 1 minus 1 out of P1 times 1 minus 1 out of P2 times 1 minus 1 out of P3 times all the way up to 1 minus 1 out of Pk, then times n. These P1, P2, P3 are just the prime factors of n. So I take one example there, this example, and the example says, find the number of units module 4,900. So the question is, how many numbers, that is the question, how many numbers are relatively prime to 4,900? How many numbers are relatively prime? So for me to do that, I don't need to list all of them. I just need to know how to factorize this number as a product of its prime factors. And this one, you can do it using any of the algorithms. When you factorize that, you will find this. You need to know how to factorize using algorithms, because this number can be even huge than this. Can be even huge than this. This is just a smaller number because I was not using an algorithm. So after that, it's 1 minus a half. You know where the 2 is coming from. And then 1 minus a fifth. The 5 is coming from here. Then 1 minus 1 out of 7. The 7 is coming from here. Then times 4,900. And this first bracket gives you a half. The second bracket gives you 4 out of 5. And this other bracket gives you 6 out of 7. Then when you multiply this, you get that we shall have 1,680 numbers which are relatively prime to 4,900. So, you know, if you are to list all of them, you will take a lot of time. But if you have this formula, it becomes very easy for us. Now, what does this question say? This question is saying, this one, the one that I have, denote the Euler-5 function by this. Find this. In other words, find how many numbers are relatively prime to 19. Find how many numbers are relatively prime to 840. find how many numbers are relatively prime to 930. The first question is very easy. 19 is prime. So we have 19 minus 1 elements, which are relatively prime to 19. And this other one, 840 is not prime. So we factorize it to find out what are the prime factors there. We have 2 by prime factor, 3 by prime factor, 5 by prime factor, and 7 by prime factor. So that one you just factorize. Just factorize. 2 goes there. 4, that 420. Then it 2 again, we go there 2, 10, I think. And then the 2 there, we go there 1 or 5. And then the 3 here, we go there, that 5. And then 5 there, we go there 7 times. Then 7 there, we go there once. So we found that we have the prime numbers 2, then we have 3, then you have 5, then you have 7. Then after finding that, just take 1 out of this 2, subtract from a half. No, subtract from 1 to get a half. And then 1 out of 3, subtract from 1 to get a 2/3. And then 1 out of 5, subtract from 1 to get 4 out of 5. And then 1 out of 7, subtract from 1 to get 6 out of 7. Then multiply n. When you multiply that, you get that there are 192 relatively prime numbers. Now, I'll not do the other one because it's just the same thing. We just factorize that 930 because it's not prime. Now, let's look at Fermat's little theorem, which we shall use to get the inverse. And this is the statement of Fermat's little theorem. It says, if P is a prime number, then any integer which is not divisible by 2, if we have any integer that P cannot divide, any integer that P cannot divide, then we can write this. Let me just repeat the condition. The condition is that P here should be prime, should be a prime number. And that P should not be able to divide A. P should not be able to divide A. If that is the case, then A raised to P minus 1 will be congruent to 1 mod P. Will be congruent to 1 mod P. Now, this expression can also be rewritten. Let's see how to rewrite it. We can also rewrite it using the law of indices. Because using the law of indices, we know that when somebody writes P minus 1, this is the same as writing A raised to P out of A. That is the same. So that means if I say it's congruent to 1 mod P, then I can multiply both sides. Now, supposing this is not here, this is just equivalent to that. I can multiply both sides by A to get A raised to P is congruent to A mod P. So that is why I say you can also rewrite it this way. So the Fermat's little theorem, it's either this, you can write it that way or this way. But what is important is that P must be prime and P must not be a number that can divide A. So let's just look at examples of where do we apply Fermat's theorem. Now, so look at this. We've been doing this. Just a minute. Let me just 1 minute. Okay, so we've been looking at this. We've done these questions before. And let me just remind you what this question means. We've done this question. So the question is, what is the remainder if 19 was to divide this number? This is what it means when you write A mod M. It means that A is the remainder after dividing by M. So that is a question. The question is, find 2 raised to 1982 mod 19. Or what is the remainder when that? Now, we had done this question earlier using fast powering algorithm, but now I also indicated that Fermat's little theorem combined with the fast powering algorithm makes this working easier. For us to use the Fermat's little theorem, we only need to find out whether this 19 is prime and whether this 19 cannot divide it 2. So if those 2 conditions are met, then it means we can use Fermat's little theorem. Now, for this question, the 2 conditions are met. So let's use the Fermat's little theorem. What does it say? It says that if those 2 conditions are met, then 2 raised to P minus 1 will be the same as 1 mod P. That's what Fermat's little theorem says. Now, so what do we have here? What we have here is 2 raised to 18 will be congruent to 1 mod 19. Now, this is a very important statement because from here, we can now write the answer to this initial question straight away. We only need to compare the powers. The power here is 1982, and the power here is 18. And as we were doing earlier, we then use division algorithm to write 1982 in terms of 18. Because the power here is 18, the power here is 1982. So using division algorithm, you write 1982 in terms of 18. So 18 would go into 1982 110 times, and the remainder will be 2. So what then means, what this means, and I want just to do it straight away from here. What it means is that if I'm asked to write 2 raised to 1982, I can write it as 2 raised to 18 raised to this thing, 2 raised to this thing, because this thing is 1982. It's 18 multiplied by 110 plus 2. And this one can be written as 2 multiplied by 18, no, raised to 18 multiplied by 110 times 2 raised to 2. When you use the laws of indices. And so this is the same as 2 raised to 18 raised to 110 times 2 raised to 2. But I know what 2 raised to 18 is. 2 raised to 18 is 1 from here. 2 raised to 18 is 1. So this is the same as 1 raised to 110. And this is 2 raised to 2. And so what is the remainder therefore for answer? This is 2. 1 raised to 110 is just 1. And this is 4. So that means the question, this question, the answer is 4. And I don't want to be going through all these steps. So if I don't want to go through all these steps, I just come back here. Coming back here, noting that the remainder is 2 after this division algorithm. Noting that the remainder is 2. And you can see that 2 here. You can see that 2 is here. The rest has given us 1. This other part has given us 1. This other part has given us 1. Has given us 1 here. So what we are only left with is this remainder, 2, raised to this 2 here. So this 2 was the remainder. This power here was the remainder. So let me just clear this and show you then how I would have done it easily. How I would have done it easily, I would have said, using the Fermat's little theorem, 2 raised to 18 is congruent to 1 mod 19. Then write 1982 in terms of 18 as that plus 2. So my solution, therefore, becomes these 2 here, raised to this remainder, which is 4. 2 raised to that remainder. So this is the remainder when 19 was to go into this. I've used Fermat's little theorem, and you can see it has made our work easy. I want to do the last question, use Fermat's little theorem, and then we'll stop at that. Again, I want to find the remainder when this number is divided by 17. This number is divided by 17. I note that 17 is prime, and 17 cannot divide 8, and therefore Fermat's little theorem can be used. And Fermat's little theorem says that a raised to 1 minus p should be congruent to 1 mod p. So p in this case is 17, and a in this case is 8. So that means 8 raised to 16 is congruent to 1 mod 17. So now, having reached here, I write this 1,000 in terms of 16, because 16 is our power here. So 1,000 is the same as 16 goes there. How many times? 16 goes there 62 times, and the remainder is 8. So therefore, I know that this will give me 1 if I proceed. So the answer therefore is 8 raised to 8 mod 17. Because 8 is the remainder. This remainder here is my power. Now, so this is now the one I'm supposed to work out. This is the one I'm supposed to work out. So this one now, since 17 is bigger than 8, I would use the first powering algorithm to do this. So 8 raised to 1 is 8. 8 raised to 2 is 64. 64 mod 17. The remainder will be 13. 64, if 17 were to be 64, that one just use a calculator. Let me just use my calculator and see whether that is correct. I also use yours. So that is 8 times 8 is 64. So 64 divided by 17 I get 3 point something. So what is the remainder? The remainder is 13. Now I want to reach 8 raised to 8. So what about 8 raised to 4? 8 raised to 4 is just 13 square. So 13 square times 13 square is 169. Divided by 17, you get 9 points. So what is the remainder? The remainder is 16. 16 is the same as -1. 16 is the same as -1. Because you remember I said it's always good to make this number as small as possible. It's the same as -1 mod 17. So now, what I now want is 8 raised to 8, which is the same as this squaring this. I'm using fast powering algorithm, square this. So squaring -1 is just 1. So that means the answer to this question, therefore, the remainder when 17 is divided into this number is 1. 1 is the answer to that question. So that is how we use the Fermat's little theorem to get remainders when a number is divided into such numbers. So next time we shall now be using the Fermat's little theorem to find inverses. Thank you. I think next time is tomorrow, the same time.
Yes, thank you very much, Mwalimu. Yeah, I guess I don't know if there are any questions. All right, so the recording will be made available. It will be shared in the group this evening. So I'll see you guys tomorrow in case there are no questions.
The notes, huh?
Oh yes,
The
also
notes
Mwalimu, kindly, yeah.
The notes I had already shared in the last lesson. I shared up to this bit. The one I shared on Thursday, yeah, already has this bit.
So I think there's a question.
Okay.
So Frank is asking, how do you use algorithms to calculate powers for large numbers? And that's in the chat.
Oh, the questions are in the chat. Huh?
Yeah.
Let me see if I can open it. Oh yeah, I can see the one by Clinton. Is there WhatsApp group? Okay, that one is not the question. Hello, Doc. Where is that? The one shared by who?
Frank. Just
Frank.
scroll down to the end.
There is that, Frank. I have 2 questions. How do you use algorithms to calculate powers for large numbers? Okay, so we need to come up with those algorithms. And I think Wanjiru will be assisting them in doing that, those algorithms later, during maybe Wednesday and so on.
I think when everybody was asking how you use an algorithm to calculate the power of a large number. So a good example is what happens if the EVM machine when they are hashing, it's called hashing actually. So what happens is there's an operation called the key-substitutive speed that converts whatever input you give it into an output of numbers, a valid input of numbers, output of numbers and figures that cannot be deciphered by anyone other than the one who has actually a public key to decipher what you've given. So depending on the EVM, that is how we use it to find the power of a large number. And it's also dependent on its use. Yeah.
And Frank had said he had 2 questions, but I've seen one. There's only one question that I'm seeing there. So maybe the other one he'll ask later, maybe during the class when Wanjiru will be explaining to them. But I'll also try and maybe send you the algorithm. So when you have the algorithm, you're just inserting those numbers. And when you insert, and then it gives you the result. So the thing is, how do you then come up with that algorithm? Because once you have the algorithm, you just put the numbers, you put the base, you put the power, and then you put the divisor, and then it gives you the result. So maybe what he's asking maybe is how to come up with such algorithms. Maybe that is a question he wanted to ask. Thank you.
Okay, awesome. So we'll call it an evening if there are no more questions. Thank you, everyone. See you tomorrow.